All right, so let's take a look at Chapter 17. Chapter 17 is of huge importance. You have two probability models that we discussed, the binomial probability model, which we're going to start with, and then we're going to take a look at the geometric probability model as well. Okay, so anytime you're using the binomial probability model or the geometric probability model, what I need to think about is Bernoulli trials. In essence, there's three components to Bernoulli trials. You're going to see me check those three components in question one, and then it's going to get repetitive. I'm not going to continue to check them. I might verbally talk about them, but on an AP exam, if it's a free response question, checking those three conditions is something that could make your score round up if you're like at a 2.5 or a 3.5. Okay, so take a look at question number one here. Basketball player made 71% of his foul shots during the season. If he shoots 10, what's the probability he makes exactly 6? So I need to figure out, is this geometric or binomial? Obviously, because it's listed under binomial, I kind of gave it away. But the difference between the two models is in a binomial probability model, it's a certain number of trials, a certain number of successes in a fixed number of trials, in this case, 10. Where a geometric probability model is how long until the first success. So I don't know how many trials that could take. Okay, so this is why it's a binomial probability model. So is this a Bernoulli trial? There's three components that needs to be met. One, the probability of success is constant. Yes, it's 71%, it's not changing. Two, there's two outcomes, success and failure, making the foul shot and missing the foul shot. Three, each event is independent. So the probability that he makes one shot has no bearing on the probability that he makes another shot. Those three components are met. So this is an example of a Bernoulli trial. All right, so I need to start by identifying a random variable here. So this is building on what we saw in chapter 16 dealing with random variables. So I have that capital X is equal to the number of shots made out of 10. That's, again, what makes it a binomial probability model. I have a specific number of trials, 10. Okay, so I'm going to identify what probability model I'm using. X is binomial, and binomial has two parameters, the number of trials, 10, and the probability of success, in this case, 0.71. And this would be expected on an AP exam. Okay, so what's the probability he makes exactly 6? I need to understand that these formulas are on my formula sheet. X has a binomial probability distribution with parameters n and p. If you forget, it tells you there's two parameters right here. So I'm going to be using this formula. It's the probability, in this case, that x equals 6. So I have the probability that x is equal to 6. Okay, so kind of referencing this formula here, it's n, that was my parameter, the number of trials, choose k, so it's 10, choose 6. I just said there's 6 successes. P was my probability of success. That was 0.71 to the k. K is how many successes, so in this case, 6. 1 minus p, that's going to be 1 minus 0.71 is 0.29. And the exponent is n minus k. N is the number of trials, 10. K is the number of successes, 6. 10 minus 6 is 4. Now, there's two ways I can calculate this on my calculator. I will show you both. One is to do second distribution. I'm going to go to binomial PDF. PDF because I just have an exact amount. I just have one formula here. The number of trials, comma, probability of success, comma, and then the number of successes. All right. If you forget how to do that, you can do something similar to that you learned in Algebra 2 trig. I can go to 10, math, probability, choose 6, and type this in 0.71 to the 6th and times 0.29 to the 4th. Okay? I would prefer that you use the top method. We talked about this pretty much exclusively in class, and you should be comfortable with this, but this would kind of be a backup. Okay, in either case, there's about a 19% chance of that happening. Okay, so that's question one. Let's take a look at the question, this next question here. All right, an archer is able to hit the bullseye 60% of the time. Assume each shot is independent. So they came right out and told you that here of others. If she shoots 10 arrows, what's the probability of at most 7 bullseyes? Okay, so again with the Bernoulli trials, the probability of success is constant. There's 2 outcomes. You hit the bullseye, you don't. And each shot is independent. Bernoulli trials, we're good. Trying to figure out, is it a binomial probability model, is it geometric? I have a fixed number of trials, 10. That is not changing. That makes it a binomial probability model. So I'm going to start by identifying a random variable again. X is, I'm trying to measure the number of bullseyes hit, so it's the number of bullseyes out of 10. Always, 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 if it's a binomial probability model, when you identify the random variable, put the number of trials here. Number of bullseyes out of 10. X is binomial. As I saw on my green sheet a minute ago, if you need to see it again, binomial distribution with parameters n and p. I have 2 parameters, the number of trials and the probability of success, so 10 and 0.6. Okay, so the probability of at most 7 bullseyes. So this is going to represent an inequality here. So I have the probability that X is less than or equal to 7. So that means it could be 0 all the way up to 7. At most, you're writing 3 formulas. So I'm referencing this formula again. I'm not going to talk through it explicitly like I did in the previous example. If you need to, get out your formula sheet, pause the video, see if you can write out the 3 formulas I'm going to write out. This is going to be 10 choose 0. That's the n choose k. P to the k. 1 minus p is 0.4. N minus k. 10. Plus 10 choose 1. 0.6 to the first. 0.4 to the ninth. Plus dot dot dot. Plus, then my last formula is going to be 10 choose 7, 0.6 to the 7th, 0.4 to the 3rd, equals. Okay, so going back to the calculator here, I'm not going to be able to do binomial PDF because I have more than one formula. If all else failed and you needed to, you could add up those 7 formulas, but that's a waste of your time. So I'm going to go to binomial CDF, cumulative density function. Still the number of trials, the probability of success, but the last number that I put in, it's going to sum up all of those successes. So I want everything less than or equal to 7. So I'm going to put in 7 there, and what that's going to do is that's going to add the probability of 0 successes plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, which is what we want. Okay, 0.590. So a little bit over a 59% chance of that happening. Okay, so let's look at part C, or question 3. An archer was able to hit the bullseye 60% of the time, assuming each shot is independent. Okay, so I didn't get too creative with the scenarios here. Very similar to what we just saw in the previous example. So it's Bernoulli trials, the whole 9. It's binomial because there's a fixed number of trials here. So identify a random variable. X is the number of bullseyes out of 10. We need to include that number of trials. X is binomial. You have 2 parameters, n and p, 10 and 0.6. Now, here's the difference. At least 7 bullseyes, at least. So when I'm writing my inequality now, it's the probability X is greater than or equal to 7. Okay, so 3 formulas is what I need to write. So I'm going to start at 7. So I have 10 choose 7. P to the k times 1 minus p to the n minus k. Again, I'm using the formula right off my green sheet here. Right here. Plus 10 choose 8. 0.6 to the 8th. 0.4 to the 2nd. Plus dot dot dot. Plus my last formula is going to be 10 choose 10. 0.6 to the 10th, 0.4 to the 0. Okay, so taking a look at the calculator. It's going to be a CDF anytime you're not starting at 0 successes. In this case, our first formula was 7. I need to do 1 minus. Then I'm going to go to binomial CDF. Number of trials, 10. Probability of success, 0.6. And remember what I said in question 2. I need to subtract whatever number I put here. It's going to add up all of those successes. Well, I need to get rid of 0 through 6 successes, leaving me with just 7 through 10. So I'm going to put a 6 here. Kind of shortcut is it's literally one number less than you're starting at. I started at 7 successes. I put 6 here. If this was greater than or equal to 5, this would be a 4. Okay? So this is 0.382. So my probability of getting at least 7 bullseyes is a little over 38%. Okay, so those are a couple examples with the binomial distribution, and exactly, at most, at least. Those are pretty much the scenarios that you're going to see. Okay, taking a look at the geometric probability model now. And what we have here is basketball player made 64% of his shots during the season. Probability, and find the probability that in tonight's game he misses for the first time. This is the key component here. Misses for the first time. That's the difference between the geometric and the binomial probability model. The geometric probability model is how long until the first success. Yes, we're identifying as a miss as a success here, but it's how long did it take. That's why we don't have a fixed number of trials. So Bernoulli trials, yes. Probability of missing is constant. Probability made is 64%, so the probability he missed is constant as 36. He either misses or he makes it, so you have success and failure, and each trial is independent of one another. It's not changing. Okay, I need to start by identifying a random variable, as we have done. X is now the number of shots until the first miss. Why miss instead of make? Because I want to find the probability he misses for the first time. X is geometric. It's the geometric probability model. This is not on your green sheet anywhere. So you need to know that geometric probability has one parameter, and it's just your probability of success. I need to be extremely careful here. I'm not going to put 0.64 because I'm talking about the probability he misses. So it's going to be geometric with a parameter of 0.36. So if I'm saying the number of shots until the first miss, I'm saying the probability that X is equal to 6. Okay, so I have 5 makes and then a miss. So this is kind of similar to what we saw back in chapter 14. So the probability that he makes it, because each shot is independent of one another, I can multiply these events. So 0.64 to the 5th times 0.36. And I can plug that in my calculator pretty easily and get 0.0837. So a little less than a 4% chance of that happening. Okay, let's look at question 2. Bowler throws a strike 62% of the time. Each throw is independent. What's the probability? Again, throws his first strike within the first 4 shots. We're only interested in that first strike. I don't have a certain, this is not a fixed number of trials. It's not saying out of 4 shots, how many strikes does he get? That would be binomial. Okay? So this is going to be geometric. Well, let me identify the random variable first. So x equals the number of shots until the first strike. That's what I'm interested in finding. X is geometric. We have a parameter of, so I'm looking for the first strike. He throws a strike 62% of the time. So X is geometric with a parameter of 0.62 within the first 4 shots. So what I need to realize is it could happen on the first shot, or the second, or the third, or the fourth. So I have the probability that X is less than or equal to 4. So if he strikes on the first shot, that happens 62% of the time. Or his first strike could come on the second shot, which means he didn't strike and then he got a strike. Or he could not strike twice and then strike. Or he could not strike the first 3 shots and then get a strike. Okay, I can plug this in my calculator. When I do so, I'm going to get 0.9791. There's about a 98% chance he's going to get his first strike within the first 4 shots. Okay, let's move on to some other questions with chapter 17 here on the next page. Okay, so we're going to start to build off of that a little bit into some expected value and some standard deviation questions. So in question 3, suppose a computer chip manufacturer rejects 4% of the chips produced because they fail pre-sale testing. If we select 50 chips at random, how many chips do you expect to test before finding a bad one? So we're looking how long until that first success. This becomes a geometric probability model. All right? So I know that X equals the number of chips tested before the first bad one. Number of chips I'm testing before I get the first bad one. I know that X is geometric, and I have one parameter, 0.04. Now, I'm talking expect. I'm thinking about expected value. I'm thinking about expected value for geometric. As I look at my formula sheet here, I have binomial. I have some stuff listed here. Then it gets into random samples. I don't have anything about geometric on my green formula sheet. It's not helpful. This is a formula you need to know that's not on your green formula sheet. This is your expected value for a geometric mean. It's 1 divided by p. So in this case, it's 1 divided by 0.04. I need to check 25 chips on average before I'm going to find a defective one. Okay, so next question. Assume 13% of people are left-handed. If we select 120 people at random from the cafeteria, how many lefties do you expect? Okay, I have a given sample size here. Well, I did in the previous one, you might be saying. True, but it's how many do you expect before finding a bad one? It's again, how long until that first success? Okay, how many lefties do you expect? So this is binomial. It's Bernoulli trials. Probability of success is constant. You're left-handed or you're not. And then each person being left-handed is independent of one another. So identifying a random variable here. X equals the number of lefties out of 120. Then I have X is binomial. Formula sheet, in case you forgot. 2 parameters here, N, P. 120, comma, 0.13. How many do I expect? Well, that's expected value. Let's check out the green sheet here. Binomial distribution. There is expected value right there. Mean of x, that's just a different way of writing expected value of x. N times p. Well, those are my parameters, n and p. I can simply calculate that. So I have mu sub x, or you could write expected value of x in either case equals n 120 times p 0.13. So in this case, calculating that, 15.6. I expect about 15.6 lefties out of 120 people. Okay, part B, I want to now know the standard deviation. Well, take a look at the formula sheet again. Here we go. Standard deviation, binomial distribution. Here we go. Square root of np times 1 minus p. So that formula is there for us. So as I'm calculating the standard deviation, sigma sub x, or standard deviation of x, equals the square root of n, 120, times p, 0.13, times 1 minus p, 0.87. And that's going to calculate to give me 3.68. So I have 3.68 lefties for my standard deviation. All right, part C. If we keep picking until we find a lefty, okay, we keep going until we get that first success. How long do I expect as an expected value it's going to take? So you should be thinking to yourself, all right, how long until that first success? We're talking about a geometric probability model right now, so I need to identify a new random variable. Because I'm still within this question, I'm on part C, I'm not going to pick x, because that I identified for a binomial variable, or a variable that we use the binomial distribution, probability distribution for. So I'm going to say y is the number of people until the first lefty. Okay. And I know that y is geometric with a probability of success of 0.13 by one parameter. This is the formula I went over at the top of this page, number 3. It's not on your green sheet. You do need to know this for your AP exam. It's simply 1 divided by p. In this case, 1 divided by 0.13. So I expect to check on average about 7.69 people before I encounter the first lefty. Okay, is the normal model appropriate here? Sometimes you can use the normal model as an approximation for the binomial probability model. And if you remember, that hinges on one condition. It was the first condition we started talking a lot about. It's the success failure condition. So, in essence, what I need to know is this. Are NP and NQ greater than or equal to 10? If so, my sample size is large enough and I can use the normal model as an approximation. So, N was 120, P was 0.13, that was 15.6, we calculated that up above. 120 times Q, Q is just 1 minus P, if you need to see that. You will never see Q on your green sheet, your formula sheet, it's always listed as 1 minus P. So times 0.87. If I do that calculation, 104.4. And these are both greater than or equal to 10. So the answer is yes. Okay, taking a look at this last page here. I'm going to take a quick cough break. Okay, so kind of continuing on where we left off, we just said, yes, we can use the normal model as an approximation for the binomial probability model. So now it's saying, would you be surprised if we found 23 left-handed people? Okay, well, if you think back to the previous page, we calculated a mean, we calculated a standard deviation. So we had a mean of 15.6. And our standard deviation, let me double check that, was 3.68. Now, I can only use this if that success failure condition is met, and it was. So now I'm going to use the normal model as an approximation for the binomial probability model. So I have a normal model with a mean of 15.6 and a statistic now of 23. Would I be surprised if we found 23 left-handed people? Well, I'm thinking an upper tail. I'm not just interested in exactly 23. I need to see 23 or more. How unusual is that? So I'm going to be calculating a z-score here. My statistic is above the mean. This is going to be a positive z-score, so 23 minus 15.6 divided by 3.68. As I do that calculation, 23 minus 15.6 divided by 3.68, I get a z-score of approximately 2.011. So I want to be as concrete as possible in my answer, not something big like, yes, it's unusual, it's more than 2 standard deviations away from the mean. I can take this a step further and get that actual probability. Okay, if I do a norm CDF in my calculator, and I do 2.011, comma 99, I have 0.022. So would I be surprised? Yes. Why? There's a 2.2% chance that I see 23 left-handed people out of 120 or more. So yes, that is pretty unusual because this is low. Think about a p-value. I mean, if it's less than 0.05, we consider it unusual. Same kind of idea here. Okay, F, what's the probability of finding at least 20 left-handed people? So we're going to take and kind of do something similar to what I just did in the previous one. So I'm going to kind of split this into 2 parts. I'm going to show you using the normal model, and I'm also going to show you using the binomial probability model. So starting with the normal model, we still have the same mean and standard deviation as above. Now I want at least 20 left-handers, still with a mean of 15.6. My statistic is 20, and I'm shading that upper tail. So I calculate a z-score, 20 minus 15.6 divided by 3.68. Again, I'm going to have a positive z-score because my statistic is above my mean. Okay, we got a z-score of approximately 1.196. Using norm CDF, I'm not going to show this. I will just verbally explain norm CDF from 1.196, comma 99. And that's going to give me 0.116. So about an 11.6% chance of finding at least 20 left-handed people out of 120 using the normal model. Now, let's take a look at if we were to use the binomial model. Okay, because the normal model is just an approximation for the binomial model. All right, so I need to identify a random variable, or no, I wouldn't, because I already identified one in the previous page. On the previous page, we said x was the number of lefties out of 120. That's not changing. So now what I need is the probability that x is greater than or equal to 20. I'm just going back to this formula again that I've used a couple of times here. N is 120, P is 0.13. I'm going to be using this formula here. So I have 120, N, choose K. My number of successes, 20. P is 0.13 to the K, 20. 1 minus P is 0.87. N minus K is 100, plus 120, choose 21. P is 0.13 to the K. 1 minus P, when I subtract those, I'm getting 99, plus dot, 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 plus. I'm going to go all the way up to 120, choose 120. P to the K times 1 minus P to the N minus K, 0. You would absolutely positively not have time to type this in using PDF plus PDF plus PDF on the AP. So let's talk about the shortcut here on your calculator. All right, so what I want to do is I want to go binom CDF. But wait, I'm starting at 20. Anytime I'm not starting at 0, if you remember back to what we said earlier, I need to do 1 minus. So I'm going 1 minus, go to second distribution, CDF. Number of trials, 120. Probability of success, 0.13, comma, number of successes. Well, I need to get rid of everything below 20 because I'm starting at 20. So I need this to sum up 0 through 19. Remember, the shortcut is it's 1 less than the starting value. So 0.145. 0.145. Okay, so comparing this to what we got when we did the normal model, they're going to be close. They're going to be a little bit off because keep in mind the normal model is just an approximation for the binomial probability model. So you can only use the normal model as an approximation if your success failure condition has been met, and that's what it's saying at the bottom, and we did that on page 5. So hopefully you guys found this helpful and you feel uber confident with probability. I'll see you in class.